Hi, everybody. So we've been talking about reflection and refraction and how light bends when it goes through any kind of different medium, any kind of denser medium than a vacuum. And we call that refraction. So one of the prime reasons that we want to be interested in refraction is because of the concept of lenses. And as we mentioned last time, lenses are a big part of our world. Anytime you need to focus light, project light, any kind of thing like that, your camera and your cell phone, all of that's going to rely on lenses. So what we're going to do today is we're going to figure out how to determine, first of all, where does the image that's produced by a lens, where is that going to be? What kind of magnification am I going to get? And how does that depend upon the properties of the lens? And then finally, we're going to talk about the lens maker's equation, where we're able to figure out, okay, if I want a specific focus, a distance, a focal length there, how do I curve that lens to give me the shape that I need? Let's get started. Okay, when we think about lenses, there are really two different kinds. There's convex lenses, like you see right here, and a concave lens that we'll look at in just a minute. The easiest way to tell the difference is in the word. A cave means it's going to go inward like this. So a concave lens would look something like this, whereas a convex lens would look something like this. Now, oftentimes we'll take two of these and we'll put them next to each other. And so this would be a double concave lens, and this would be a double convex lens. In most cases, the width of it, the thickness of it, is considerably less than the radius of curvature, this curvature that you see here, or equivalently the diameter of the lens here. And so we can assume that the light that comes in here only gets bent once, and it's going to get bent basically at that center line right there. This is called the thin lens approximation. So let's use that and see if we can figure out what's going to happen to these light rays. So let's switch over to red. So here I've got this light ray coming in, and it's coming in at some normal to the surface here. So we know that it's going to get bent, and it's going to get bent towards the normal. And so that means it's going to be bent something like this. This one that's going straight through, well, it's directly normal to the surface, and so it's going to pass straight through and bent. Same thing over here. I'm going to get bent towards the normal, and so I come like this. And of course, these other two lines will come in here too, but we're going to try to keep our diagram a little bit simple. So this distance from the center of the lens to this point where those rays come together is called the focal length. And we usually use the symbol F for that. Now, I know that's also frequency and a lot of other things too, so you really got to be careful to keep up with what these symbols mean. The focal length is nothing more than the distance from the lens to the focus. And when you focus your camera, or when your eyes are focusing, what you're trying to do is you're trying to get all of those rays to come together. Anywhere else, if I switch back to black here, anywhere else, those rays from that object are going to be kind of spread out and it's going to look kind of fuzzy. So the focus is always going to occur where those lines come together at a point. Okay, so this is what we would expect to see from a converging lens. So a convex lens is also called, and most of the time is called, a converging lens because the light rays converge on each other to a focus. So on the other hand, the other type is that concave lens. And you remember that the concave lens means that I'm forming kind of a cave right here. All right, same idea here. This ray comes in and it's going to get bent towards the normal. So it's going to go off this way. This ray is coming at the normal, and so it's going to go straight on through. Whereas this ray, here's its normal to that surface. It's going to get bent towards that normal. And so you see that the light rays are going to spread out. So what controls how much of these bending basically is what? The index of refraction. So the greater that index of refraction, the more the bending that I'm going to have. And remember that we can make these lenses out of anything that we want. We can make them out of light, we can make them out of glass for light to go through it, but we can also make them out of water. And that's something that maybe you have experienced because that's how your eye works. So let's go ahead and delete this page. And let's take a look at this. Now, you may say, well, why on earth would I want to spread out the light? Why would I want to defocus the light? Well, actually, these concave, these diverging lenses are the single most common lens in the world because that's what you probably have if you wear glasses. If you're nearsighted, then what's happening is that you can see in the diagram down here, technically nearsightedness is called myopia, but what's happening is that the light is focusing too far ahead. And so the image that ends up on your retina, and remember that's what you're actually going to see, that's going to be all fuzzy. So what we want to do is we need to find some way to move that focus back. So what we do is we pre-bend the light. So when you put this is your glasses here, the light spreads out. So it's now no longer coming in parallel the way it is here. So since it's coming at a more extreme angle here, we're going to get this bent even more. And so now your eye, the lens of your eye, which is a converging lens, then is going to focus it right there on the retina. So by adjusting the focal length of this diverging lens, then you can correct for any errors. Your lens is actually made of fluid in your eye, and so it's not glass or anything like that. It's the fluid being held in there. If you wear contact lenses, it's doing the same thing, but now the shape of the lens is actually floating on your eye, and it's filling with the moisture, filling with the tears that are in your eye. And so instead of using glass, it's actually using moisture. So another example that we would use is if we want to focus a beam. So let's say that I want to get a nice parallel beam of light coming through here, and I've got an incandescent light source. Well, incandescent light, like just a regular old-fashioned light bulb, it's sending it out in all directions. So what happens then is I can put a converging lens here and run it in reverse. So if my light source is directly at the focus of that lens, and that's really important, we're going to see why in a minute, but if that light source is at the focus of the lens, then when it comes in, it's going to be bent so that it's parallel. And so this allows me to collimate the beam, we call it. So it turns it into a column instead of just randomly spreading out everywhere. So by focusing that beam, making it into a column, then I can concentrate the energy, and as such, I'll get a brighter light. And so this is often used in flashlights, so that if I have an incandescent bulb or even an LED, which is going to put out incandescent light, then it spreads out, but the collimator is going to make it so that it stays focused more into that column, into that beam, and then that's going to concentrate that energy there. Okay, so if we want to figure out what's happening, though, up to this point, we've been assuming that the light coming in was parallel to each other. And if the light is coming from infinity, that's actually true. So if the light comes from far enough away, those light rays are going to be parallel. The classic example of that would be a star. So a star is putting out, here's my star, it's putting light out in all directions. However, the star is so far away from you that you only receive the light from this tiny, tiny little piece here. The rest of it misses you here on Earth. So basically what you get from the star is going to be very, very close to being parallel. You may have also heard about focusing your camera at infinity. Really what that means is we're focusing the camera so that parallel light rays, if they come in straight like this, they will be focused directly on the camera film or the sensor if you're using a CCD camera, a digital camera. So what if, though, the light is not parallel? And for any realistic thing that you're looking at, your computer screen or your friend or anything like that, they're too close. And so the light is not going to be parallel. It's certainly not going to be parallel from that. So what we want to do is we want to trace these principal rays. So here's two rules that we're going to use for determining what happens to these three principal rays. These rules you really want to memorize. They are very, very important. And if you memorize these and memorize the three rays, you're going to be able to do pretty much everything you need to do. I'm going to take a side note here. We're talking about ray optics, remember, but don't forget that it is an electromagnetic wave. And so when we're talking about a ray, what we're really talking about is the direction of propagation of those wavefronts as it's moving through. So still, don't think of it as being a beam, a laser beam or anything like that. It's an electromagnetic wave. And what we're doing is we're using that propagation direction to make the geometry a little bit easier to follow with that. Okay, so Here's our two rules. Light rays that pass through the focus, and by that we mean on either side. Let me get my picture here where we can see it. So light rays that pass through the focus. So if this is the focus, right here, then or here, anything that passes through that will be perpendicular when it comes through. And that's what we've seen up to this point. If I have something that is perpendicular to the lens, and this is going to be my lens surface right here, then it's going to go through the focus. And that's going to be true on this side as well. But by the same token, remember, this is a double convex lens. So that means I have a focus on this side as well, because you can think of it as having two of these kind of D-shaped lenses right next to each other. So I've got a focus on this side. So if I have light that comes from here, for example, it's also going to come out parallel. So it's going to get collimated, just like we talked about before. Okay? So that's what we mean when we say any kind of light ray that passes through the focus will be refracted, so it's perpendicular to the lens. I want to be real careful. We're using this thin lens approximation. So when we derived how that was moving, we looked at the normal to this surface here. However, now we're going to assume that this thing is so thin that the light just passes through, and we're going to measure everything from the center of that lens. The curvature is determining where it focuses. That is definitely happening. We can't just replace this by a sheet of flat glass. However, once we've determined where that focal point is, now we can say, okay, we're going to do everything from the center of that, and I don't have to worry about the actual curvature. Later on, we're going to figure out how we can find that curvature that will give us the focal point we want. All right, so that's our first ray. So the second rule is a ray that passes through the center of the lens won't be refracted at all. Well, that should make sense, right? If I'm coming in through here, I'm normal to the surface, even to this point, this center line that I have right here, so no refraction can take place. So those are our two simple rules. If I have something parallel to the lens, then it's going to get refracted through the focus. Could probably done a better job of that. Then it's going to get refracted through the focus, or equivalently, if it's coming through the focus, then it's going to come out parallel. And that can be in either direction. I've drawn it on this side simply because that's where our dude is, our image, our object that we're going to use to project our image from this. Okay, so let's say that I want to know what is the image that's going to be produced by this guy right here. All right, so he's standing in front of the lens, and he's obviously not at infinity. So the light rays that are coming from him are not going to be coming in parallel to each other. For a star, remember, they are going to be parallel. And this is why a star will never appear as anything other than just a dot. It doesn't matter how much you try to magnify it. Because those rays are parallel, it's a dot. That's it. The guy that we have here, though, is obviously not a dot. So here's our rules for determining our three principal rays. So there are three rays that I can draw that will determine everything about the image. So I can have a ray that travels parallel to the lens axis. So that's what we were talking about. It's coming in parallel, then we know that that's going to get refracted through the focus. I can have a ray that passes through the center, straight on through. I can have a ray that passes through the focus on the same side of the lens as the object. And so those were those three cases that we drew here. So let's do our principal rays in different colors. Let's do this way. Okay, so if I've got red, so I could have one principal ray, looks like that. Now, I want it to launch from the image because that's what we're going to be interested in plotting. So rather than just draw it in some, mythical space, let's say I want to picture where is the top of his head. Now I can do this process for his entire body and I can reconstruct it for everywhere. But if we do it at the top of the head, you're going to be able to see what's going on. So imagine that I've got a light ray. One of my principal light rays is coming out from his head and it's coming in straight. So based on our rules, if it's coming in parallel to my lens axis, so it's coming in orthogonal, normal to our center line of the lens, how's it going to be bent? It's going to be bent right onto the focus. So it's going to come down like this. All right. Let's choose a different color. We'll go with purple. Now the next ray, scrolling up here where you can see it, the next ray says a lens that passes through the center of the lens is our second principal ray. So in this case, then, I've got a ray that's going right through the center of the lens like this. Now, you may have said, oh, wait a minute, what, Dr. K, why didn't you go through this part right here? Well, yes, that certainly goes to the center. But remember, we're interested in the light that's coming from the top of his head so that we can plot the image there. So you see how my ray is going right through that center. All right, and then finally, our third ray is a ray that passes through the focus on the same side. So here, it's going to pass through the focus. What is it going to do? Let's make that actually a darker blue there so we can see what's going on. So it passes through the focus. What's it going to do when it exits the focus? Based on our rules, if it goes through the focus, then it's going to come out parallel to our center line. It's going to be orthogonal to the center line of the lens. So you can see that all three of these rays converge in the same spot, and that spot must be the top of his head. So that's his head right there. And you see that because that's the top of his head, his feet, though, are still, and this is the clue that we're giving you here, the feet toes are exactly on the center line. And they also pass through the focus, don't they? So let's draw our principal rays for that. And you're going to see that that one's actually kind of a trivial case. But if I have red here, so here's his feet. We're going to look at the light coming from his foot. It's passing through the focus. Well, that means that it needs to get bent parallel. Well, it's already parallel, so it just passes right on through. In the case of a light ray that's going through the center, well, his toes are also going through the center. So it's going to go straight through there. And then finally, if I have a light ray that passes through the focus on this side, well, guess what? It's also in the same spot. So his feet are still going to be on the center line. Once I have any two parts of the object there, I can plot what the image is going to look like. So we launch some light rays from his head, and we launch some light rays from his feet, and we can see where they get plotted using our principal rays. So what's the orientation of the stick figure on the other side of the lens? So on the image side, it's going to be inverted. So, and this is true anytime you look through some lenses, and we're going to learn that the rule is as long as I'm outside of the focal point of my lens, it's always going to be inverted. And we're going to see when we start talking about telescopes, whenever you look through the primary lens of a telescope, everything's actually upside down. And however, let's keep in mind that we're also working in 3D. So I don't want to draw his hands sticking out because they'd be coming out of the page and into the page. But you should see that the same thing's going to apply. And so his left hand, hard for you to see in the camera view, but his left hand is going to go across the lens and it's going to look like his right hand. So the image is not only going to be inverted, it's also going to be reversed. Okay. Well, we won't spend too much time with that right now because it's very difficult to draw this in 3D. We're going to have way too many lines and rays going through here. But keep that in mind. Not only is it going to be inverted, it's also going to be reversed. All right, so let's go to the next page. Now, lenses don't just make vertical images, as we said. It's going to extend out, so it's going to be reversed. But now we said that it's going to be inverted if the object is very far away from the lens. If it's outside of the focal point, then we're sure that it's going to be inverted like this. What happens if it's inside? All right, so let's do the same thing. So here, let's zoom in on this. Here we've drawn our three principal rays. So for example, I'm going to launch one from his head right here. And that's going to be based on our rules. If it comes in parallel to the surface, parallel to the center line, which are to the ground, which of course is going to be orthogonal to the center of the lens, it gets refracted through the focus. One that goes through the center line of the lens, we use purple for that. That doesn't get diffracted. That doesn't get refracted. It moves straight on through. And then finally, we said, okay, what if I have one that comes from the focus? Well, now the focus is behind him. So, but I still want it to go through the top of his head. So it's going to go this way, and then it will get refracted
so that it is orthogonal to the center line of the lens or parallel to the ground, orthogonal to the thickness of the lens, but parallel to the ground here. Okay, so where's the image? And that seems kind of weird, right? Because they don't intersect. So does that mean I don't see an image at all? Well, actually, what we have to do in this case is we trace these rays back to where they would have intersected. And that's what we're showing you here. So let's start off with this ray right here. Our first one went like this. So if we trace it back, it looks like this. And I'm going to make this a dashed line because the light ray never actually went through that point. Remember, the light ray came from the dude's head, so that never actually moved through here, but we're going to trace that back like that. All right, how about the next one? So our next one was the one that went right through the center line. Whoops, we want that to be purple. It went right through the center line. So I'm going to trace that back, and you see that it intersects up here. And then finally, our third principal ray went through his foot this way, or went from the center through his head this way. And so if we trace that back, it comes right back. So you see that they do intersect, but they intersect on the same side of the image. If I'm standing back here looking at it, so this is me, and I'm actually looking at the image, it looks like the person standing in front is much larger, and it looks like he's standing in front of the lens. And so this is kind of a spooky effect where you can actually pass your hand through the image and all that. Your brain thinks that the image is there. Your brain constructs where those light rays would have been. However, they're not really there. And that's one of the kind of cool things about it. If I took a screen and I put my screen right here, nothing will be projected on it. Whereas in the previous case, when my dude was standing here, and he was outside of the focal length. Oops, let's have that go through the center. So here's my lens, right? And then we're going to have our dude standing right here, but he's going to be outside of the focal length, outside of the focal point. Then in that case, the rays actually did converge down here. And so clean that up just a little bit. So if I were to put a screen right here, I would actually get an image on the screen. It would be projected on the screen. And this is how cameras and movies and all that other sort of thing work. There's actually light intersecting here, but there's no light intersecting here. So for that reason, we call this a virtual image. It only appears there in your brain, because your brain is actually reconstructing where those things can run. Whereas this one, where the light rays actually did go through the image, we call that a real image. Okay, that's going to be a very important distinction, is to keep up with whether it's a real image or a virtual image. Okay? And a good rule of thumb, as you'll see in the text, is actually hidden by the camera right now, but a good rule of thumb is if the image is formed on the same side as the object, it's probably a virtual image. And we can do that by seeing that the rule, though, is not the light rays never actually went through that point. Therefore, it's a virtual image as opposed to a real image. So you won't get anything projected onto a screen. All right, let's take a look at the microtext then. What is the orientation of the image? Let's get rid of our little adjustments here. What is the orientation of the image produced by this guy when he's close to the lens? So here he is right here. He's close to the lens. He's inside of the focal point. Well, in that case, he's going to be upright. What did we say the orientation of the image would be when it was far away from the lens? Look back on the previous page if you don't remember. Well, then it's going to be inverted. So there must be some point at which the image flips. So starts off, I'm far away from the lens, and then the image is going to be inverted. As I get closer and closer and closer, at some point it's going to flip, and now it's going to be upright. So we want to figure out where that occurs, and I bet you can probably guess where that occurs. So at what distance do you guess that is going to happen? At what distance do you think that flip is going to occur? Well, we said that if he's inside that focus, if he's inside that focal length, then he's going to be inverted. If he's outside, then he's going to be upright. So the focal point, which by the way is also called the focus, those two things mean the same thing. So at the focal point, that's going to be the flip point. So let's summarize that what we've had. What does the image look like for an object that's very close to the lens? It's going to be upright. And so if it's very far away, if it's outside the focal length, it's going to be inverted. The distance at which it flips, and D is going to be our distance to the actual object. That's going to flip at the focal point. So F, remember, we defined to be our focal point. So here's my lens. When the light rays come in, they get focused. That distance right there is going to be F. And of course, I have one on this side as well. It's from the light rays coming through here. So if I am closer to F, closer to the lens than F, then I'm going to get a virtual image. Same thing would happen on this side of the lens. And if you think about it, that makes sense. I'm looking at you instead of you looking at me. There's no real difference there. Okay, so we want to find a mathematical expression for when this occurs. So let's come up with some symbols. I'm going to zoom in on this so that you can see it. Let's come up with some symbols that we're going to use for the rest of our discussion about lenses. So this distance, we've already said this distance from the object to the lens, and remember, we're going to measure everything from the center line of the lens. We're going to use the letter D. So D is going to be our object distance. You'll see some places they use an O to represent the object distance. Whatever works for you. Remember, we can use any symbols we want. The distance from the center of the lens to where the image forms, we're going to call I. Now, this is not a current or anything like that. This is going to be the distance from the lens to the image. Okay? The height, the actual height of the object, we're going to call H0. So remember, that's the real height. That's how tall it really is, 6'1" or whatever it happens to be. The height that it appears on the image, we're going to call HI. Notice that we've called this one negative. That's because it goes in the opposite direction from my actual image. So in the case of when I'm in close, so if this is my focal point and I'm right here, remember that my image is way back here. But now my HI is going to be positive because it's in the same direction as my original object. Okay? So keep those sign conventions in mind because they're going to make a big difference when we start plotting things. Okay. So let's go ahead and delete this one. So we want to start trying to get some idea of the math that's going on here. So we're going to zoom in on our little image here. And I've labeled some more points for you, just so that we can all talk about the same one without having to gesture and point. So this point right here, from where we're having our light ray leave from the top of his head, we're going to call A. Notice that I've only drawn 2 of the principal rays. It turns out you should be able to plot any image just using 2. Did you see that? You remember that our third ray went through that same point. So you could pick any 2 of these 3 principal rays and you'll be able to draw where the image is going to be. Which 2 should you pick? Well, of course, it's going to be the ones that make it easiest. So just know you have those 3 rays available. I could have it here. I've chosen the one that goes parallel to the ground or perpendicular to the image, to the lens center. And then I've drawn the one that goes straight through the center. But I could do the same thing by having one go through the focus on this side here. Oops, let's move that back. By having one go through the focus on this side here. And then you would see that I would get the same thing if I pass through the focus, then it's going to end up going through the same part of the image. So I can use even 2 of these 3 rays. Okay, we've chosen these 2, so those are the ones that we're going to stick with for this. All right, so we want to relate the size and where this image is going to form to where the object is. So to get started with this, how does the angle ADB, but that's this angle right here. How does that compare to the angle GDF, which is this angle here? There's a couple ways you can think about that. If you remember some geometry, there's some shortcuts, but let's think about that. Well, let me switch to red here. Since this is perpendicular to each other, right? Then I have alternate interior angles here. And anytime I have alternate interior angles, there is a geometry proof that says those angles are going to be equal to each other. So these two angles have to be equal to each other. And that kind of makes sense if you think about it, right? So I've taken this and I've cut it in half. So this is my right angle, and this is a right angle, and this is a right angle, and this is a right angle. So any way that you divvy it up, you're going to find that this angle is going to be equal to this angle. All right, so now let's see if we can figure this out. Oops, that's not the one I wanted. I wanted that one. There we go. So if I can show that I have two sides and an included angle, or equivalently, if all three angles are the same, then I will have similar triangles. So we've already decided that this angle and this angle are the same. How about this angle right here? Well, that's a right angle, right? How about this angle? And so just to remind ourselves of which triangles we're interested in this triangle, and we are interested in this triangle. Okay. So that's a right angle, and that's a right angle. So what can you say about this angle right here? It must be 90 minus our little angle here. Same thing here. This angle must be 90 minus this angle. Well, if this angle is equal to this angle, and both of these are 90 minus that, then it must also be the same. So I've got three angles that are all the same. That tells me that these triangles must be similar. Now, be careful. It does not mean that they're identical. Does not mean that they're identical. It just means that they're similar. And so by that, we mean that they're the same shape, even if they're not necessarily the same size. Let me draw what that means. So I might have this triangle and this triangle. And you see that they're similar, but they're not exactly the same. You can think of it as having a scaling factor. So if I magnified this, if I multiplied this, all three sides by the same scaling factor, then I'll end up with this triangle right here. That's the definition of similar triangles. If we hadn't realized that this angle and this angle were equal to each other, we could certainly say that ABD and DGF have to be the same because they're right angles, right? Let's go back to red so that we can see that. Those are right angles right there. So those are certainly the same. And then we know that side BD, which is this side, must be proportional to this side. And we know that AB and GF must be proportional to each other. So that also satisfies the definition of similar triangles. So you can go about it any way that you want. I think if you remember the idea of this alternate interior angles, I think that actually makes it easier to see that those triangles do obviously have to be similar, because now I can prove directly that all three angles must be the same. Okay, so let's erase this and let's move up our picture here. So if they are similar, zoom out just a little bit. So if they are similar, then we said that the sides have this scaling factor. So what that means is that the ratio of AB to FG, let's do that in red so we can see it. The ratio of AB to FG must be equal to the ratio of BD to GD. Think about what that means. Remember, we're just magnifying or reducing one triangle. They're the same triangle, just different sizes. Well, if this one is proportional to this one, then, so say this one, we've put our scale factor to be 50%. So this one is 50% the length of this. Well, then this must also be 50% of that. So proportionately, they're going to have to be the same. Okay, and so that's our scale factor between the two of them. Now, it can get kind of confusing to have to deal with these two-letter names that are identifying our sides, A, B, and BD, and all that other sort of stuff. So let's replace that with the variables that we've defined before, this H0, HI, D, F, and I. All right, so let's go to the next page. And we need to move that one out of the way. There we go. So now we've got our same picture, and we're gonna express all of this in terms of the same variables that we've defined for this. Now let's remind ourselves of the proportions that we found. We found that AB and GF, that's our scale factor. And since it's the same scale factor, that must also be true for BD. And then in this triangle, it was DG. So now let's rewrite that using our symbols. Well, AB is going to be H0. GF is going to be minus HI. BD is going to be our object distance D. And DG is going to be our image distance I. Okay? So that's our first step. Now what we're going to do is we're going to use two other triangles, and we're going to get this same ratio, this D over I. And we're going to use that to get our final result. So the other similar triangle that we have is CDE, so that's this one, and EFG, that's this one. And here again, we can prove it the same way. You see I have alternate interior angles, so those two must be the same. Those two angles must be the same. And then I've got two right angles here. So those are obviously the same. And then this must be 90 minus the small angle, and this is also 90 minus the small angle. All three sides have the same angles. Therefore, they're similar triangles. Okay, so let's write these same ratios then. So now we're going to use CD must be proportional to what? What's the equivalent one on this side? That's going to be GF or FG. Choose whichever you like, right? And then I know that DE must be proportional to EG. So again, two-letter names are confusing, so let's go ahead and use our symbols here. CD is also H0. Do you see that those are exactly the same? So that's H0. And GF is also going to be our minus HI. So far, so good. What's different here is this. The distance from D to E that we have right here, let's do another color for that so we can see it. This distance here, now what is that? That's going to be our focal length. That's going to be F. Let's keep that in black so that we can still see it. So that's going to be equal to F. And now I also want E to G. Now that one's maybe not quite so obvious. If this entire distance is I and this part of it is F, how would I write just the part from E to G? Well, that's going to be I minus F, right? So I know that these two are the same, okay? Now, we've got this scale factor, this ratio, this H0 over minus HI. And remember, those scale factors are the same. So my scale factor for these is the same on all four parts of this. The reason we're going to get rid of the object height is because we want to come up with something that depends only upon the lens and not based on what we happen to be looking through the lens. So this is going to give us some important properties of the lens. So since both of these, D over I, is equal to this fraction, they're both equal to the same thing, they must be equal to each other. So DI must equal F over I minus F. So those two expressions are equal to each other. Okay, I'm going to scoot this to the side for just a minute so that we can still use it. If I can get my computer to wake up. There we go. Now, technically, we're done. We've got the expression that we're looking for, but we want to maybe clean it up just a little bit. So I'm going to leave this here long enough to copy it down so that I don't have to keep this page up. So we've got D over I is equal to F over I minus F. All right, let's go ahead and delete this page then. And now we can zoom in on this page here. Okay, so let's rearrange things so that we can get what we want for this. And I'm going to flip through my pages on this side so I can make sure that we're following along here. All right. Okay, so first of all, let's go ahead and let's flip both sides because I want to get this minus sign up on the top, okay? So that gives me that I over D must be equal to I minus F over F. And what we're going to do is we're going to solve this for 1 over F and see what we end up getting, okay? So let's break this fraction apart. So my I over D is going to equal I over F, that's an I, minus F over F, which is just 1. Let's make sure that we're all following along with that. Right? So I over F minus F over F. And that's why I needed to flip it so that I could break this fraction apart here. So that is simply equal to 1. Okay? Now I'm going to multiply through, or I'm going to divide through by I so that I can get this 1 over F by itself. And so now I get 1 over D is equal to 1 over F minus 1 over I. See what we've done there? We've divided all three terms by I. Well, we said we wanted this in terms of 1 over F. So I get 1 over F, I'm just going to bring this to the other side, is 1 over D plus 1 over I. And this is called the lens equation. So there's a couple of things that I can do with this. Let's move this out of the way. There's a couple of things that I can do with this. If I know where my object is and I know where my image is, okay, well, now I've got the focal length. In many cases, though, what I actually want to know is where is the image? And so I would say, okay, I know what the focal length of my lens is because it was just given to me. And then take 1 over that minus 1 over D, where my actual object is. That will give me 1 over where the image is formed. So then I can just flip it and do that. Okay, now we derive this for a converging lens, for a double convex lens. The same thing holds for a converging lens. We could go through the same arguments, go through all the same triangles. The only difference is that, remember, now my image is on the same side as my object. And so that means then that I is going to be a negative number. And so the end result then is that F is going to be negative as well. My F will end up being a negative number from that. And so if you are nearsighted, your glasses will have a negative diopters, a negative measure of curvature there from that. So the focal length is going to actually be negative. You'll see that as we start to work more with diverging lenses as well as converging lenses. Okay, so another useful quantity then is going to be the magnification. And this should be fairly obvious. Let's zoom in on this so that you can see it. This should be fairly obvious. The image, this is the actual height of my image, and this is my object, and this is my image height. If my image comes out to be twice as big as my original, so 2HO over HO, those cancel out and just leaves me 2, then we say that the magnification is 2. On the other hand, it is possible for my image to come out to be smaller than my original. And if that happens, then let's say that maybe it comes out to half the size of my original. Well, then that again cancels out, and my magnification is just going to be 1/2. So this way I can define how the image appears relative to the original object. If it's bigger than 1, okay, well then it's going to be magnified. If it's going to be less than 1, it's going to be reduced. The last thing we want to talk about is it inverted or reversed? Well, remember that if the image is reversed, is it image upright or inverted? If the image is inverted, like the case where we had with the converging lens, you remember that this worked out to be where my image here we said was negative. So what that means then is if I put a negative sign here, then I'm going to get a negative. Let's suppose that it's being reduced to 1/2 size, for example. Then that just comes out to be a negative. So the negative sign here tells you whether the image is going to be inverted or if it's going to be upright. with our converging lens that we have here, and we're far away from the focal point here. So my image, the magnification is going to be negative because it's inverted. So that's just a rule that you can remember, but it comes out of the fact that we defined that to be negative because of the way we oriented our H. Okay, let my computer catch up here so that I can move. There we go. Okay, now we could also write the magnification in terms of the object distance. Do that below. Now remember that D and I are going to be in the opposite direction. So what would that work out to be? Well, our magnification then must be somehow related to the image divided by the object distance, the image distance divided by the object distance. However, remember that it is in the opposite direction if it's for our converging lens. So if this was my lens, right, this was my object distance here, my image distance was on the other side. And so that would be negative as well. So this would be my magnification then in terms of the image distance and the object distance. If I'm being magnified, well, then that image distance is going to be greater. If I'm doing reduction, then it's going to end up being smaller, but the magnification will be the same. The reason we might want to do this depends upon what you're given in the problem. If I'm given the object height and the image height and I need the magnification for some reason, say I want to figure out where is that image going to be formed, well, those magnifications are going to be the same. On the other hand, if I know the distances, like for example, suppose I know the focal length of the lens and I know where my object is, I can use that to find the image distance. Once I know the image distance, then I can find the magnification and I can tell how large the image is going to be up here. So by manipulating these two different definitions, the magnification, the two different definitions for the magnification, and our lens equation, which was 1 over f is 1 over d plus 1 over I. Using those three equations, we can generally solve pretty much any optic system, any lens system that we want to work with. Okay, so now we're ready to look at our scenario here. So it says, suppose we have a lens with a focal length of 0.40 centimeters. So remember, that's going to be 0.40 meters. And an object is viewed from a distance of 14 centimeters. So right away, this should be able to tell you something about what we expect to see from the image. We are inside the focal length. What's it going to look like? So keep that in mind. It's always good to know the answer before you try to find the answer. So we want to know what is the magnification. So we want to find the magnification given the focal length and the object distance. Well, okay, since we've got the focal length, we know we're going to use the lens equation because that's the only one we have that uses the focal length. But we also want the magnification. So we want to use the magnification then that depends upon the object distance. So remember, we've got two different versions. So we know that we're going to use this version of the magnification. Let's go ahead and write down our symbols then. Our focal length f is going to be 40 centimeters, so that's 0.40 meters. Our object distance is 14 centimeters, so that's going to be 0.14 meters. And what we want is m, which of course has no units. Now, we know that we're going to eventually need I for this, right? Because that's already in our plan. However, it's good practice not to add any symbols in until you need them, because you never know. There may be things may cancel out or something like that. So to start off with, we're going to need an equation to get m. Find an equation that gives you your answer first, and then see if that introduces new symbols. Well, we've already decided that that's the equation we're going to use. And this is adding in a new symbol, I. So I'm going to put this over here. That's our image distance, and we don't know what that is. So this is saying, we're saying, hey, this equation will give me m. And the problem is saying, okay, well, if you give me I, I'll give you what you're looking for. So your task now is to find an equation that gives you I. Well, our plan is we're going to use the lens equation. So we know 1 over f is 1 over d plus 1 over I. We did not add any new symbols here. So I've got two equations and two unknowns. I'm good. The problem solved. Everything else is just going to be algebra. All right. So let's move this over to the side so that we can see what we're doing here. We'll zoom out just a little bit. And let's go ahead and combine these two then. So we're going to always start with the one that has what you want to find. So what we want to find is m. So we know m is minus I over d. And then I'm going to use this equation to plug in for I. Now, you could logically say, well, okay, I think I want to find I first, and I'm going to find a number for that then I can put in. And if you're on an exam, hey, if that's what occurs to you first, go with that. But what we're going to see is if we wait to combine, to put in numbers until we have all this, everything in terms of symbols, we're going to find out something interesting that we can actually use later. So we need to find I here. So I'm going to solve this equation for I. That's going to be 1 over d plus 1 over I. Okay, so I'm going to subtract this out, and I get 1 over f minus 1 over d is equal to 1 over I. Now, I could actually go ahead and invert this if I wanted to, and you would get something that looks like 1 over 1 minus 1 over f minus 1 over d is equal to I. And if you're going to plug in numbers, sure, that'll work. It's ugly. You're going to have to be really careful with your parentheses, but it would absolutely work. But let's see what happens if we don't do that off the bat. First of all, let's combine these two fractions. So that means I need to find a common denominator. So my common denominator is just going to be FD. So that's going to be D over FD minus F over FD must equal 1 over I. Let's double check to make sure that works. My D's cancel, my F's cancel. D's cancel here, I get 1 over F. F's cancel, I get 1 over D. I'm good. Now that they have a common denominator, I can subtract them. So D over minus F over FD must equal 1 over I. Well, that then tells me that I must equal FD over D minus F. Here again, you might say, okay, I've got what I want. I'm going to plug in for I, and then I'm going to put it back in here. Let's wait. If I plug what I have here back into this expression, then I get minus FD over D minus F times 1 over D, because I'm dividing by D. And notice what happens. The D's actually cancel. And so now I found that the magnification is negative F over D minus F. And that's an expression that I can use later. That's an expression that I can use anytime I want to find the magnification, but all I have is the focal length of the lens and the distance of the object. And guess what? That's almost always what we have in a real world situation. I've chosen my lens. I know what its focal length is because it was manufactured to that. I've put it in my system, and I've got my object standing right here. Figure out what the magnification you're going to get is. Simple as that. So we're going to have call to use this. So this is one you might want to write down your flip book and have ready to go. All right, so now we've got what we want. We're going to plug in our numbers. So I get minus F is going to be 0.40 meters. This D is on the object side, so it's going to be positive. That's going to be 0.14 meters minus 0.40 meters. When you work that out, then we're going to get a minus sign overall, but this is going to be negative in the bottom. And so the end result is I'm going to get a positive 1.54. Go through the work, see if you get the same thing. Now that we've got that, so does the image appear larger or smaller than the object based on the magnification you just found? Well, it's bigger than 1, so it's going to be larger. Is the image going to be upright or inverted? Well, because it's positive, it's going to be upright. Now that matches what we expected, because if I had my lens here and we said, if this was my focal length, if my object is inside that focal length, then we got a virtual image. And so that virtual image then in this case was going to be larger and it was going to be upright. Matches what we knew. Okay, now suppose we're using the same lens, but now we're going to look at an object farther away. What if the distance is 1.5 meters? What's the magnification? Here's an example where you've already worked out your expression. We can just plug straight back into that. So M then is going to equal minus F over D minus F. My focal length is the same, so that's negative 0.40 meters divided by, now my image distance is 1.5 meters minus 0.40 meters. All my meters cancel as they did up here because my M must be dimensionless. And when you work that out, you get negative 0.364. Put that in your calculator and see if you get the same thing I do. Pause the video and make sure that you do this because you will have to do this for the exam. All right, based on this then, does the image appear larger or smaller than the object? It's going to be smaller because my magnification is less than 1. Is it upright or is it inverted? It's going to be inverted, right? And that makes sense. Again, we said that if this is my focal point and my object guy was back here, then the image was going to be smaller and inverted. So that matches what we predicted when we did our ray tracing before. Okay. What is the magnification going to be when the image appears to be actual size? Now, m equals 1 is obvious, right? However, what may not be obvious is that m equals minus 1 is also actual size. So at that point, it's actual size but inverted from that. So make sure you keep in mind that there are two actual cases here. All right, so let's look at the next scenario then. If I can get my pages to delete because my computer is running slow. All right, so we want to know at what distance then does that object appear to be actual size? And we said that that means it's going to be m equals 1. So we're going to have two possibilities here. I could have the actual size at m equals positive 1, and I could have actual size at m equals minus 1. And we can use this expression that we derived before. So my quantities here, I don't know what d is this time. I do know the focal length, and the focal length was 0.40 meters. And then my magnification, though, is going to be either 1 or minus 1. We're going to have to work it out for both cases. Let's use the same expression that we just derived. So m is going to be negative f over d minus f. All right. Now on your page, you've got room to do this on step 5 on the other. I'm going to do it off to the side here as we often do. So let's do the first case where m equals 1. And so I'm solving for d. So let's go ahead and solve this equation. And so I get m times d minus f must equal minus f. And so md minus mf must equal f. I want to get my d by itself, remember. So I've got md is going to equal mf plus f. I'm going to factor out my f here, and that gives me 1 plus m times f. And then finally, I'm going to divide by m. So d equals, I'm just going to write it as m plus 1 since that looks neater to me, times f. Okay, so we've got two cases where this can occur. So let's take the positive case first. So when m equals 1, so the image is now upright. So the image is upright, and that tells me that d occurs at 1 plus 1 over 1 times my focal length. So that's twice my focal length. And that's going to be a general result. I will always get, as you can see here, I will always get the object to be actual sized when I'm at a distance at twice the focal length. So there's my lens. Here's my focal length. So when I'm at a distance of twice the focal length, I'm going to get it actual size. So in this case, it's going to be 2 times 0.40 meters. Or in this case, it's simply going to be 0.80 meters. Okay. Now, what about the other case? Because this also could work. So if m is minus 1, then I get minus 1 plus 1 over minus 1 times f. But this then is 0. So this is at a distance of 0 meters. So on the lens, it's also going to be actual size. And if you think about it, well, okay, that's what we call the trivial case. That makes sense, right? If I've got my object actually sitting on the lens, it's not going to look magnified at all. It's just going to be the object sitting there. So that makes sense, but it's the less interesting case. So both of these are valid answers, but this is the one that's going to work, that's going to make the most sense for us. Okay, so there's one more case that we want to consider. Up to this point, we've assumed, okay, I've got some lens and I know what the focal length is, and I just treat it basically as a very, very thin piece of glass. But what if I want to make a lens that has a specific focal length? So this is what your optometrist has to do. The optometrist has figured out what focal length you need in order to correct for your vision, but somebody's got to make that lens. So that means we can't ignore the curvature on each side of the lens here. And we're going to do this for a convex lens, but the principle of the procedure we're going to go through would be the same for a concave lens as well. So look at the diagram that we've got here. And something that might get a little bit confusing here is we're going to talk about the radius of curvature. But when we talk about the radius of curvature, let's get a different color here. We're talking about, like, for this lens, imagine that I had an entire sphere here. I don't. I've only got a tiny little piece of it. But if I had drawn that whole sphere, my radius of curvature would be the radius of that sphere. Now, notice that the radius of curvature, the radius for the right half of the lens, is on the left side of the diagram. So don't get confused by that. All right. It's going to be one lens, but we're going to treat it separately. We're going to treat each side separately. Okay. So starting with the R1 side here then. So the ray coming from O, from our object in the diagram, is going to be normal to this surface here. So basically based on our ray tracing, what is going to happen to that light ray? If it hits perpendicular, normal to the surface, to the glass, how is it going to get bent? No, it's not going to be bent at all. So it would continue on out this way. All right, so that ray would just continue straight on through. We're going to you'll see why we're putting this together here in just a minute. Okay, now the upper ray, let me go ahead and erase this part. Now the upper ray is coming in parallel to the center of the lens. So it's going to strike that lens when we're talking about this surface right here. It's going to strike that at some angle from the normal. So it strikes at this angle here is going to be theta I. We'll make that a little bit bigger so that you can see it. And then it's going to get refracted. Here's our normal to the surface of the lens. And then it's going to get refracted away from that normal, some angle theta R. Right? So what is Snell's law for the right half here that we're talking about when the ray leaves the lens and enters the air? Well, that's going to be N, in this case, is going to be my incident angle. That's going to be we've decided N is inside here. And if we're going to be in air, right, the index of refraction of air is just basically 1. It's 1.0003, but to 4 significant digits, we can treat it to be the same. We can just treat it to be 1. So N of our glass, we're just going to use N for. Okay, so that's going to be, since we're in the glass, that's going to be my incident angle. So that's going to be sine of theta I. And then that's coming out in air. What's the index of refraction of air? It's going to be 1. So that's going to be sine of theta R. That's going to be my refracted angle. All right, now for any realistic lens, the angles here are going to be very small. The radius of curvature is going to be much larger than any kind of thickness, any kind of amount of time that I'm moving through here. So we can use the small angle approximation. If you don't remember what that is, that's worth Googling, but that's something that you're going to use quite a bit. So the small angle approximation says that sine theta is approximately theta. You can test that on your calculator. Choose a very, very small angle, 0.0001. Take the sine of it, and you're going to see that you get 0.0001. So if we use that approximation, if we replace our sine thetas with thetas, then I'm just going to get this. And I could have left those signs in, but now I'm carrying around a lot of trig functions that I don't necessarily need. So that's going to be Snell's law, in this case, because I can use the small angle approximation. Okay, now I've got my pages organized where I want them. So we want to find the angle from the horizontal that the outgoing ray is bent. All right, taking a look at our diagram here, that angle from the horizontal is this one right here. And a little fuzzy to read right there. But if this angle is theta I, and this angle is theta R, then this angle right here must be theta R minus theta I. Why is that true? Well, remember that, let's use red here. We said that this line was normal to the surface. And then I have this line coming in here. So because there are alternate interior angles, we've used this before, then if this is theta I, then this must also be theta I because they're alternate interior angles. So this angle right here is also theta I. This entire angle here is theta R. So the smaller piece that's left is going to be theta r minus theta I. Step through the angles and make sure you follow that. Maybe pause the video and make sure that you see that, because you won't get the rest of it otherwise. So this line goes straight through, right? Because it hits it orthogonal. So it's going straight through. So this must be theta I, and this must also be theta I. And then my angle of refraction is the whole bending angle here, but my horizontal is coming from this ray right here. And so that angle there is going to be theta r minus theta I. Okay, so let's plug that back in over here. And so we have theta r minus theta I. But I'm going to plug in the result we got on the previous page, that n theta I was equal to theta r. And let's use that to get rid of my theta r. So let's just plug this in for theta r right here. And that tells me that n theta I n theta I minus theta I then is what that value is. And so I can factor out my theta I. And so that angle is n minus 1 times theta I. Right? So that's the value of that angle, that outgoing ray that we have right here. So this angle from the horizontal then must be n minus 1 times theta I. Okay, let me erase some of this so we can talk about some of the other triangles that are here. So the triangle formed on the right side of the lens, and by that we mean, oops, my pen's not cooperating. There we go. By that we mean this triangle right here, right? So it has sides of length F1 and H. Let's make sure that we understand why that's F1. So this length here is the focal length as it moves through this lens on this side. Do you see that that's where it's going to be focused? So if I have my parallel light rays coming in, like this, and remember they got bent and they got focused right here. So the distance from the center of the lens to that focal point, that must be the focus of the right half of the lens here, of this, the left part of the right half of the lens that's got my left side curvature, if that makes sense to you. Okay. I keep putting notes in here that I don't really want to put in. There we go. So this then is the focal length of this side over here. So we'll call that F1. And then obviously this triangle length is going to be H. Let's put that in red so that we can see it. So that's H, and that's going to be F1. Okay. All right. So what we want to know is, how is this angle related to this angle? And we'll zoom in on the page here so that you can see it. So how is that angle related to those two sides? Now, these two angles must be the same. And this is another theorem from geometry, that if I have parallel lines here, and I have a line that goes through those parallel lines, then this angle and this angle are going to have to be the same. If you don't remember all these trigonometric identities, then it's probably worth looking up. But for the most part, you can just, if you can accept that that's what they are, then we'll move on from there. All right, so that means that this angle right here must also be theta r minus theta I. And we decided that that was equal to n minus 1 theta I. So how is that angle related to H and F1? Which trig function is going to give that to me? Well, that one's going to be the tangent. And so the tangent of, we'll start off by saying theta r minus theta I must equal the opposite over adjacent. So that's going to be H over F1, like that. All right, and so now we will substitute in what we found here above. So this pen doesn't want to cooperate. So this is equal to the tangent of n minus 1 theta I. Now the small angle approximation holds still, and another form of the small angle approximation, just like sine theta equals theta, tangent theta also equals theta. By the way, cosine theta does not equal theta, but cosine theta is going to be approximately 1. But so this tells me that tangent of this function, tangent of this theta r minus theta I, is approximately theta r minus theta I. So I have h over f is going to equal theta r minus theta I, which we said is now equal to this. So we have this function right here. And so theta r minus theta I is equal to this. So it is n minus 1 over theta I. So when we set them equal to each other, then we finally have h over f is equal to n minus 1 times theta I. All right. Now let's clear this out so that we can see it. Now the triangle formula on the left side is this one, right? And its sides have length r1, the radius of curvature of this side, and then this is also going to be h from here. Okay, so how is that going to be related to this angle right here? Now this angle is theta I because this angle is theta I. And for the same reason that we had before, I've got these parallel lines, I've got a line coming in through between them, so these alternate interior angles here then are going to be equal to each other, right? So I've got a triangle, I've got R1 here, I've got H here. What trig function is going to form those? That's going to be the tangent again. So the tangent of theta I must equal H over R1. We're going to use a small angle approximation on that. So tangent theta is approximately theta. So that gives me theta I. It's going to be H over R1. Now, finally, we're going to use this to eliminate our theta 1 from the above function that we have there. So I'm going to plug it in up here. And so I get H over F must equal n minus 1 times H over R1. And here we're going to simplify this. And since H is just some arbitrary point that we're using, right? It's just some arbitrary object up there. So we need this equation to hold for anything because the lens maker, the optometrist doesn't know what the height of the thing you're going to be looking at. But fortunately, they do in fact cancel out. And so I'm left with 1 over F is equal to n minus 1 times 1 over R1. And so that's the first half. That's just using 1/2 of the lens. All right. Now we can do this for the other half, and we're going to get something very, very similar. Let me zoom out again, hopefully. My computer will wake up. There we go. So we can repeat that for the right half. We can repeat that for the left half of the lens, and we'll get exactly the same thing, but we're just going to substitute in our 1s for 2s. So writing down what we had here, we had 1 over F. Let's just zoom up here where we can see it. 1 over F is n minus 1 times 1 over R1. So times n minus 1 times 1 over R1. So our equation for the other half is going to be same thing, 1 over F equals n minus 1 over 1 over R1. Now, here we were a little bit sloppy. That's the focal length of our first lens. This is the focal length of our second lens. Okay? So each equation will allow us to find the focal length for, let's just go ahead and delete this right quick. That will allow us to find the focal length of that particular half of the lens that we're looking for. So we're going to combine those then. So what are the only two? Let's go ahead and rewrite what we've got here. So we have 1 over F1 is equal to n minus 1. N, and remember, is the index of refraction of the glass. 1 over R1. And we know 1 over F2 is n minus 1 times, times 1 over R2. So what are the only two properties then that are going to determine the focal length? That's going to be the index of refraction, n, and the radii of curvature. Okay, so now we've looked at the two halves of the lenses individually. What are we going to get when we put them together? Because now that's what I've actually got, is this double convex lens here. By the way, that should be an R2, shouldn't it? Okay, so here's my two results. So let's redraw our picture here so that we can follow what's going on. So there's my lens, here's my object over here, and then here's my image over here. So this is going to be my object, and this is going to be my image. We use a capital I for that for now. So we're going to assume that the object, and therefore the light from that object, is on this side. You know, maybe I've got some dude or whatever, and its light is coming through here. And then that's going to produce an image maybe over here, right? We're not going to draw our dude because we don't know exactly where he is. Okay, so this is the normal case, what we would think of, where I've got the object on this side and I'm going to produce the image on this side. Okay, so the image is forming on the right half of the lens. What does the lens equation for the left half of the lens look like? Now, let's be very, very careful with what we're doing here. This is the left half of the lens. So we're talking about things on this side here, right? That's going to be the left half of the lens. So is that the number one side? Is this the number one side, or is this the number two side? Yeah, that's the number one side. This is the number one side over here. This is the number two side over here. So the lens equation then needs to use our subscripts 2 for the left half. All right, so our lens equation says 1 over f2 is going to equal 1 over d2 plus 1 over I2. Okay. And now, so now we want to substitute that in to what we found for the left half, which is this part right up here, because both are going to be 1 over f. So we have 1 over f2 is equal to n minus 1, 1 over r2, and that's equal to 1 over d2 plus 1 over I2. That should be a 2 there. Okay. So they're both equal to 1 over f over 2, so they must be equal to each other. All right. Now, here's where we might want to think a little bit carefully, because the image formed by the left half serves as serves as a virtual object for the right part of the lens. Think about it, because they're on opposite sides. So this image here becomes the object that's going to get formed over here. So this image becomes an object that's going to produce an image over here. But in this case, it's going to be a virtual image because my virtual image is on the same side as my actual object. Remember that was our rule. If the image produced is on the same side as the real object, then we say that it's a virtual image. Okay. So this tells us then that D1 must equal negative I2. So my object distance for that side, which is D1 for, let's do it in a different color, for this half of the lens, then, remember this is the one side, must be equal to my image distance here. And of course, that's going to be in the opposite direction, so it's going to be negative. So D1 is going to equal negative I2. See if that makes sense. And that's what we're talking about right here. It gets a little confusing because the right lens, we're dealing with all the stuff that's on in the left half of our diagram. And so that's where you have to keep coming back and forth. That's why we've drawn these 1 and 2s for our subscripts here. Okay, so we want to write the lens equation for the right half of the lens. We've already done it for the left half. The right half of the lens is this half here, right? And that half is determined by our one side. So we're going to use subscripts 1 for that. So that tells me that F1 must equal 1 over D1 plus 1 over I1, like that. Okay. This is also equal to, from this equation here, that's going to be equal to n minus 1, 1 over R1, just like we did before. Okay. So now I've got two equations. We're going to go ahead and write them down here. 1 over d1 plus 1 over I1 and 1 over d2 plus 1 over I2. Okay? So those two equations right there. Okay, now I can make this substitution here that d1 is equal to minus I2. So let's go ahead and do that. So we're gonna put that substitution in here and get my pen back. And so n minus 1 times 1 over R1 must equal d1 is minus 1 over I2 plus 1 over I1. And then this one, of course, stays the same. 1 over R2 is equal to 1 over D2. Computer's running a little slow, so it's taking time for it to draw. Plus 1 over I2. Like that. Wait, so the total refraction then is just going to be the sum of these two equations. So all we need to do is we just need to add them together. So I'm going to have n minus 1 over R1 plus n minus 1 over R2 must equal minus I2 plus I1 plus 1 over D2. This to where we can get to it. 1 over D2 plus 1 over I2. So we can simplify a little bit. You see that these are going to cancel each other out. And I can combine these two. So I get n minus 1 times 1 over R plus R1 plus 1 over R2 must equal 1 over, we'll write it as D2 plus 1 over I1 so that it fits the form of our typical lens equation right here. Okay. So if this is my lens equation, right, we said that this was equal to 1 over the focal length. But here, the focal length is the focal length of the entire lens because we've put both of them together. And think about what, if that makes sense, the object for the D2 lens, which is this one right here, this is going to be D2, I'm sorry, it's going to be this lens right here. And then my object is on that side and it's producing an image from I1. So this fits the standard formula. And this tells me then that 1 over F must equal n minus 1 times 1 plus R1 plus 1 over R2. And this is called the Lensmaker's equation. Because it's what allows us to determine how I want to grind that glass to give me the focal length that I want. And you can see that I don't have to have the same curvature on each side of the glass if there's for some reason that I don't want to do that. So, but whatever I decide that I want those curvatures to be, and if they're the same, then of course these are just going to be equal to each other. And then n is the index of refraction. So that was a really long, involved derivation, but this is the important thing. This is what you need to learn and be able to use. And all you really need to do is just understand what these different terms mean. So let me scroll up here just a little bit so we can draw another diagram. So if I've got a lens, then this side, let's do that in red, this side has a radius of curvature, and this side has a radius of curvature, and they don't have to be the same. And it doesn't really matter which one you call R1 and which one you call R2, does it? Because they're simply going to be added by the time we get done. So either one doesn't matter. You could say, if you get really confused and go, okay, I'm tired of this being R2, I want this to be R1. So by God, I'm going to make it R1. You can do that because you can use whatever symbols that you want. It doesn't matter. And it's still going to give you the same result because we're going to end up adding here. Okay, so if I know the index of refraction of my glass and I know my 2 radii of curvature, I now have the focal length of my lens. It's a lot of geometry this time, and you may be sitting here going, oh, geometry, I haven't done geometry since high school. And you may have felt a little bit lost in some of our derivations of figuring out where these triangles are. It's okay. Don't stress over that because the important thing is that you understand the results and how to use them. So the lens equation. 1 over f equals 1 over d plus 1 over I. That tells you where the d, the object, if my object distance is here, and I know the focal length of my lens, here's where the image is going to be formed. Conversely, if I know where my object is and I know where my image is, that tells me the focal length of the lens. However, that's going to be really hard to measure. So a better way to do that then would be to measure the radii curvature for each side. And of course, if it's going to be a concave lens, then my radius of curvature is going to be negative. But it's still going to work out to be the same thing because I'm going to get a negative focal length. But I can use the lens maker's equation then to get my f, my focal length. And then I can use, if once I know my object distance, and I know my image distance, I can use that to get the magnification, which will then allow me to get the relative heights. So if I know the height of my object, I now know what the height of my image is. So the only real thing you need to be careful about is keeping up with your signs. Remember that if I have a concave lens, then the focal length needs to be negative. If I'm going to have, because it's going to be on the opposite side. If I've got my convex lens like this, then my focal length is going to be positive. So be sure and try to work through all those sign conventions and do the practice. What you may find in this case with the practice is you are going to have to put in the negative signs or the positive signs. It's not just asking for the magnitudes. And that's important because that'll give you some practice in figuring out in which case is this positive, in which case is this negative. If you got any questions, be sure and let me know. We'll see you next time.